For this part, your experimental data is time and temperature. So you were heating up water, and then after removing the water from the hot plate, you were determining the temperature of the hot water every 30 seconds up to 2 minutes. And at the same time, you had cool water or water at room temperature inside the calorimeter. And you did the same thing. You determined the temperature of the cool water every 30 seconds for 2 minutes. After your 2 minutes, you transfer the hot water into the calorimeter, and now you have both waters mixed. And you determine the temperature again every 30 seconds for 2 minutes of your mixture. So what's happening when you're mixing the water, right? Remember, heat transfer, it's always happening from an object or a substance at a high temperature to an object or a substance at a lower temperature. So heat transfer always go from hot temperature to lower temperature. So the hot water will be losing heat, and the heat that the hot water is losing will be transferred to the cool water, but also your coffee cup, the calorimeter, will be absorbing part of that heat. So what you're doing with this experiment is finding out how much heat the hot water is losing, how much heat the cool water is absorbing, and how much heat the calorimeter is also absorbing. So in theory, the amount of heat that the calorimeter is absorbing plus the amount of heat that the cool water is absorbing, those two added together should be exactly the same amount of heat that the hot water is losing. Just that the hot water will be losing the heat and the cool water and the calorimeter will be absorbing the same amount of heat. So with your data for time and temperature, you need to construct a graph. Okay? So the time it's increasing by 30 seconds, that should be your interval. And then you have the temperature on the y-axis. So in my graph, it's like three graphs in the same one. You have one for the cool water, which is the one that I have with the blue dots. One for the hot water, which is the one that I have with the red dots. At a higher temperature, that should be your hot water. And then the purple one is the temperature that you have and the time for the mixture when you're mixing the hot with the cool water. So you have your graph, and from the graph, you can calculate the change in temperature. Now, you can also get those temperatures from your list. TI for the hot water is not the first measurement of temperature that you have in your table. TI is your initial temperature, and that one is right before mixing it. Okay, is the temperature, like if your first measurement of temperature is 40 Celsius degrees, that's not your initial temperature because you're waiting to mix that hot water in the cool water for 2 minutes. So the initial temperature should be the last one that you're recording for the hot water by itself. The initial temperature for the cool water is the same thing. If the first measurement of temperature that you have for the cool water is 20, and then at 60 seconds it's 19, and then right before mixing it at your 120 seconds, 2 minutes, it's 19, that's your initial temperature because it's right before mixing the hot water with the cool water. Now, the last temperature that you have in your table for the mixture, the very last one at 120 seconds, that temperature represents your equilibrium temperature, or the temperature at which thermal equilibrium is reached. If you check your measurements of temperature, probably for the last 2 or 3, you have exactly the same number. So the temperature is not changing because you have thermal equilibrium. So that last temperature that you recorded for the mixture should be your final temperature. And remember, the final temperature is for both, for the hot water and the cool water, because you have both of them mixed together. So you can calculate your delta T looking at the graph in a similar way to what I have here in the diagram. or you can use the numbers that you're copying from your tables. If it's delta T, that's the change in temperature, and you're doing that one for the hot water. Now remember, the hot water will have a change in temperature with a negative sign because the hot water is the one that is losing the heat. So the temperature of your hot water is going down, the temperature of your cool water is going up. So negative for the hot water losing the heat, and then positive for the cool water because that one is absorbing heat. So the final temperature for the hot water is lower than the initial. And then for the cool water, it's the opposite. The final is higher than the initial. So you can calculate your delta T hot. It should be whatever you have in number 3 minus the number that you have in 1. And that is going to give you a negative number. For the cool water, it's the same number that you have in number 3. But now minus your initial temperature for the cool, which is what you have in number 2. And that's going to give you a positive number. Now in number 6 and 7, okay, the change in temperature is telling you like how much heat, right? Or the negative number for the one that is losing, the positive number for the one that is gaining. Now that sign is going to determine the sign of the heat that you're calculating in number 6 and number 7. So for number 6, you're calculating how much heat the hot water is losing. Number 7, how much heat the cool water is gaining. So for number 6, you have your equation mass times Cs times delta T. So the mass is your volume of water. The hot water, you're using 50 milliliters of water. 50 milliliters of water is the same as 50 grams. So that's the mass. The Cs is the specific heat capacity for water, which is 4.18 units of joules over grams times Celsius. And that is multiplied by the change in temperature, which is the number that you have in number 4, the change in temperature for the hot water, because you're calculating the heat that the hot water is losing. Then we do something similar with number 7. Amount of heat, it's mass times Cs times delta T. The mass for the cool water is the same 50 grams because you're again using 50 milliliters. The Cs is the same number because it's the specific heat capacity for water. And then the change in temperature now is what you have in number 5. Now, what you're trying to determine with this part is the calorimeter constant, or how much heat the calorimeter is absorbing. So you can use that one as a correction when you're doing the next part. So to calculate the heat absorbed by the calorimeter, you have your Q hot, which is a negative sign, okay? Because the hot water is the one that is losing the heat. So in your equation, you have a negative sign in front of the Q hot, which means that those two negative signs are going to cancel each other. So your Q hot with the opposite sign minus the Q cold, which is what you're calculating in number 7, is going to give you the amount of heat that the calorimeter is absorbing. Remember, you have the amount of heat that the hot water is losing, the amount of heat that the cool water is gaining, right? So the amount of heat that the calorimeter is absorbing, it should be the same amount that your hot and your cool water, like hot losing, cool gaining. It's like the difference between those two numbers. If it didn't move from the hot water to the cool water, it means that it went or it was absorbed by the calorimeter. So that's what you're calculating in number 8. Whatever number you have in number 6 minus the number that you have in number 7. But the number that you have in number 6 should be with a positive sign. Okay? The one that you're calculating is a negative, but it's canceled out with the negative sign in the equation. So ideally, you should have a heat amount absorbed by the calorimeter as a positive number, showing that it's also being absorbed. Now, number 9 is where you're calculating your calorimeter constant, C-cal. To get that one, you're doing whatever number you're getting in 8 divided by the change in temperature for the cool water, which is what you have in number 5. And then in number 10, you did the same thing twice. So in number 10, you're calculating the average. So you have your C-cal for your trial 1 and your C-cal for your trial 2. You're calculating everything in the same way. And then you get your average. You're adding the C-cal in your trial 1 plus C-cal in your trial 2. And that divided by 2 will give you the average. Now, this part is where you're calculating the actual change in enthalpy for a neutralization reaction. So everyone was using sodium hydroxide as the base, and you have a concentration for that one that is 2.05. Now, the acid might be different. You have two acids, two possible acids, so you know which one you use based on the label that you have for the reactant. It's HCl, hydrochloric acid, or sulfuric acid. The concentrations are also different for both of them, so you needed to check the concentration from the label again. If it's hydrochloric acid, the concentration is 2 molar. If it's sulfuric acid, the concentration is 1 molar. So writing down your neutralization equation, you need to write down the formula of the acid that you use, plus the base, which was sodium hydroxide, and you need to determine which products you're getting from that neutralization reaction. For the experimental data, you have the volume of the acid. It's 50 milliliters. You were filling out the burette, and then you were transferring from the burette the acid into a beaker. And then you had another burette with the sodium hydroxide. In the sodium hydroxide, you were transferring 50 milliliters from the burette into the calorimeter. Now, for this part, you're not heating up anything. Amount of heat that is going to be transferred in your reaction is coming from the actual reaction. In the previous part, you were heating up water because you were determining amount of heat transfer from the hot water to the cool water. But in here, that's not necessary. The amount of heat will be coming from the actual reaction. So you have your volumes, and then number 3, you need to calculate the mass of the solution. It's everything added together. So you're using 50 milliliters of the acid plus 50 milliliters of the base because you have all of that mixed in the calorimeter. So to get the mass of your solution, you have your total volume times the density of your solution. The density is going to be determined by which solution you have. And the solution that you have is going to be determined by which acid you're using. So you have a table in your lab manual. I wrote the numbers here. A simplified version of the table. Since we're using hydrochloric or sulfuric acid, then I wrote only the numbers corresponding for those two. If your acid is hydrochloric acid, you need to multiply your total volume times the density, which is 1.04. Your volume times density will give you the grams or the mass of your solution. If you're using sulfuric acid, for sulfuric acid, the density is 1.09. So you have your total volume times 1.09. That will give you the mass of your solution. So you have the base in your calorimeter, and you are determining the temperature of the base every 30 seconds for 2 minutes. So remember, the initial temperature of the base is not the first temperature that you're recording. It's the last one that you have right before adding the acid into the calorimeter. So again, you need a graph of temperature in your y-axis and the time on your x-axis. So in a similar way of the graph that you have for the first part. So you have the temperature every 30 seconds for 2 minutes, and then for the base, that's what I have in blue. And then you're transferring the acid into the calorimeter, and now again you're starting 30 seconds, 60 seconds, all the way up to 5 minutes, or maybe less than that if you have reached thermal equilibrium. If the temperature stops changing, then you can stop recording the temperature. So you have your graph. What I have here in the pink color is the temperature for the mixture of the acid and the base, and you have in blue the temperature of the base. So your initial temperature for the base will be, you see, the last dot that I have in my graph, because that's the temperature right before mixing the acid into the calorimeter. Now the final temperature is the temperature where thermal equilibrium is reached, which means that you can use the last recording of temperature that you have in your table for time and temperature. It means that you can use the difference between those temperatures to calculate your delta T here. So to calculate the heat, you're using the same equation again, mass times Cs times delta T. So your delta T is the change in temperature, which you can calculate using your final temperature that you're recording for the mixture and the initial temperature that you're recording for the base. We can do that because we're assuming that the initial temperature for the acid and the base is exactly the same. So you can use just the temperature for your base to find out your change in temperature. Now, again, the CS, the specific heat capacity for your solution, is going to be determined by which acid you're using. In part 1, we use 4.18 as the specific heat capacity because you had water. So in this one here, what you have, it's a solution. You have your products that you're getting from your neutralization reaction. So CS, if you're using hydrochloric acid as your acid, the value of CS is 3.89. If the acid that you're using is high sulfuric acid, then the value of CS is 3.81. So you have your number 3, which is the total mass that we calculated doing the total volume times the density. And then you have your specific heat capacity multiplied by the mass, and that number is coming from the table, depending on which one you're using, and your change in temperature, which is what you're calculating in number 6. If it's the amount of heat that the solution is absorbing, that number should give you a positive number. And you should know that that's going to happen because you can look at your temperatures. The initial temperature for the base, it's lower than your final temperature, your recording for temperature when you have your mixture. So if your final it's a higher temperature, it means that when you're calculating your delta T, you're getting a positive number. If the change in temperature is a positive number, that sign is the one that is going to determine what sign you're getting for the heat that you're calculating. So the amount of heat absorbed by the solution is a positive number. Heat absorbed by the calorimeter, this is where we're using the average from part 1. So you have your C count, which is the average in part 1, and that number divided by the change in the temperature will give you how much heat the calorimeter is absorbing from your reaction. Now, if the calorimeter is absorbing heat okay? And your solution is absorbing heat. The calorimeter and the solution, it's your surroundings. Okay? The reaction is the system. If the surroundings are absorbing heat, it's because the system is releasing heat. So if you're calculating a heat for your solution with a positive number, the temperature in your solution is increasing because the actual reaction is releasing heat. The heat from the reaction is moving towards the solution, and that amount of heat is the one responsible for increasing the temperature of your solution. So the heat of your reaction should always have an opposite sign of the heat of your solution. If your solution is absorbing, it's because the reaction is releasing. When the reaction is releasing heat, that is represented with a negative sign. So you have in your equation for number 9, QRXN, it's Q for your reaction or heat that the reaction is releasing. That's why you have a negative sign right there in front of. What you have in your parentheses is what you're calculating in number 7, which is the heat that the solution is absorbing, plus what you're calculating in number 8, which is the heat that the calorimeter is absorbing. So the total amount of heat that it's absorbed by the surroundings, it's giving you the amount of heat that the reaction is releasing. That's what you're doing in number 9. Now in number 10, you have to calculate the moles of the limiting reactant. You can actually determine which one is the limiting reactant by looking at your concentrations. The base that you're using has a concentration of 2.05 molar. It's a higher concentration than the one that you have for hydrochloric acid, which is 2 molar, which means that the number of moles for hydrochloric acid are going to determine the number of moles of your product for that specific acid. So the limiting reactant will be the acid. For sulfuric acid, it's the same. You might not see it in a similar way because sulfuric acid is a diprotic acid. So the concentration for sulfuric acid is 1 versus your 2.05 molar for sodium hydroxide. So the sulfuric acid is also the limiting reactant. The number of moles of sulfuric acid that you have is going to determine the number of moles of your product in your neutralization reaction. So to calculate the moles of the limiting reactant, you have the molarity of the acid. Depending on which acid you're using, you have the molarity in the label, times the volume of the acid that you used in liters. Remember, molarity, it's moles over liters. So if you're using molarity as a conversion factor to get the number of moles, your two volumes, they have to be in liters, so the unit for volume cancels out. So you were using 50 milliliters of the acid. You cannot do 50 milliliters times the molarity. You have to convert your 50 milliliters to liters times the molarity of the acid. That will give you the number of moles of the limiting reactant. And now for number 11, what you have to do is to divide your heat for the reaction, the one that you're calculating in number 9, that number divided by the number of moles of your limiting reactant, which is what you're calculating in number 10. That's how you calculate the change in enthalpy for your reaction. If the heat of the reaction has a negative sign, the change in enthalpy for your reaction will also have a negative sign. Your reaction is releasing heat. It's an exothermic reaction. And then in number 12, you're just calculating an average. If you have two trials for this part, you're adding the delta H for your trial 1 plus the delta H in your trial 2, and that divided by 2 will give you the average.